Hope you're hungry because we're going to look at some more pancakes now. We want to look at the ideas of limiting reactant, theoretical yield, and percent yield, and how we calculate those from initial masses of reactants. So if you remember the original equation or recipe that we talked about, we said that 1 cup of flour plus 2 eggs plus half a teaspoon of baking powder would give us 5 pancakes. So we don't always have just exactly what we need in the right proportion. So let's say we go to the pantry and we discover that we have 3 cups of flour, we have 10 eggs, and we have 4 teaspoons of baking powder. So from these ingredients, we need to figure out how many pancakes we can make. And we also might want to see, what we have left over. So what we need to know is which of these 3 ingredients is going to run out first if I just keep making pancakes to use them all up. Excuse me. So what we can do is take each ingredient in turn and calculate how many pancakes would I get from that much of that ingredient. So let's start with the 3 cups of flour. Well, we said that we needed 1 cup of flour to make 5 pancakes, so that means I could make 15 pancakes if I have 3 cups of flour. Let's do the same thing for the eggs. I had 10 eggs. I need 2 eggs to make 5 pancakes, so when I set that up, I see that I can make 25 pancakes based on the number of eggs. Now let's look at our 4 teaspoons of baking powder. We only need half a teaspoon of baking powder to make 5 pancakes. So if I have 4 teaspoons, that's enough to let me make 40 pancakes. All right, so I can see the potential for each ingredient to make pancakes. I can make 15 from the flour, 25 from the eggs, 40 from the baking powder. Well, obviously, the smaller number of these 3 is the 15. My cups of flour are going to run out first. I'm going to have leftover eggs, leftover baking powder, and I'm going to get 15 pancakes. Okay, so if this were a chemical reaction, and we said that flour, eggs, and baking powder were our initial reactants, the flour would be what we call our limiting reactant because it limits the amount of product we can make, pancakes in this case, and the number of pancakes we make. The pancakes are our product. So the 15 pancakes is what we call our theoretical yield. Theoretically speaking, with these ingredients, I can make 15 pancakes. Now, we don't always get all 15 pancakes. Okay, theoretically, that's what I can get. I can get that many. But let's say we cook our pancakes and in the process, we accidentally burn 3 of them. Uh-oh, there went 1, 2, 3, and 1 falls on the floor. Well, at the end of the day, even though I had enough ingredients to make 15 pancakes, I lost some of them. These 3 got burned. Nobody's going to want to eat a burned pancake, so those are no longer useful. And the one that went on the floor, well, 5-second rule was standing. We're not going to eat a pancake off the floor. We can't use that one. So we ended up with only 11 usable, edible pancakes. That 11 pancakes is what we would call our actual yield. All right, so you can calculate limiting reactant, which is what's going to run out first. You can calculate theoretical yield. If everything went absolutely perfect and I never messed up or lost anything, how much could I get? And then your actual yield, which usually is going to be a little bit less than your theoretical yield because things happen. No matter how good you are, getting every mole of a product out of a reaction is really difficult. You have to put things in containers, things stick to the side of a container, or you're washing a product and a little bit gets washed away. So actual yield is usually a little less than your theoretical yield. If I know an actual yield, how much did I actually get out of it? 11 pancakes. And I know a theoretical yield, 15 pancakes. That allows me to calculate, what is known as percent yield. It's just the ratio of the actual amount that you got, so your actual yield divided by your theoretical yield. Okay, and then always multiply by 100 to make it a percent. So in the case of our pancakes, we got 73% of our theoretical yield. So that means that, we lost 27% of the pancakes through other means. So actual yield and percent yield. Let's look at some examples of how we do that. So the actual yield of a chemical reaction, just comparing actual to percent first. Actual yield of a reaction must be determined experimentally. That is the amount that you actually recover in a laboratory setting. And it depends on the reaction conditions. As I said, the actual yield almost always less than 100%. And if the actual yield is greater than 100%, I guarantee you that it is not because you have made more than you theoretically could. You can't produce matter. It is just that there's something else in there that's not accounted for. Usually this occurs when you're synthesizing a product that has to be washed, and the product is being washed with some sort of liquid, and that liquid hasn't been completely dried off, and it adds to the mass. So that makes the actual yield appear to be higher than the theoretical. Your actual yield should always be less than theoretical, presuming that you have a thoroughly dried, pure product. Why is the actual yield less? Well, sometimes, even though we theorize that reaction should go to completion, some of the product may not form. That can be due to other variables that may not be taken into account, such as temperature. Temperature can affect a reaction, concentration of a solution. There's a variety of factors, the atmospheric pressure or the pressure the container is under. These sort of things can affect how much product forms. Sometimes a reaction doesn't go all the way from reactant to product. And sometimes you don't expect an actual yield to be even close to 100% just because of the nature of the reaction. Sometimes product gets lost in the process of recovering it. So you make it and then you have to recover it from whatever container it's in. When you measure out a cup of flour, usually a little bit of flour is going to get spilled. You can scoop up the cup, level it off, you pour it in. There's always a little bit of flour that sticks to the cup, or you might accidentally spill a little bit on the counter. So some of the product is going to get lost as you're trying to recover it. Summarizing these topics: limiting reactant, theoretical yield, actual yield, and percent yield. The limiting reactant, or it may be called limiting reagent, is going to be the reactant that gets used up in the reaction. There's no more of it left. The others will be what we call the excess reactants. There will be leftovers of those. The theoretical yield is the amount of product that can be made based on the amount of the limiting reactant. So you're going to have to calculate sort of a theoretical yield for all of the reactants that go in, but only one of them limits the reaction. So the theoretical yield is going to be that smallest amount. Okay. So when you're calculating theoretically how much you could make from each reactant, go with the smallest amount. Okay, in terms of grams. The actual yield is going to be the amount you actually produce in the chemical reaction and recover. Okay, so it's the recovered mass in grams. And then the percent yield is going to be the actual divided by the theoretical times 100. Now this seems fairly simple and straightforward, but there's a lot of things to keep track of in these examples, so be sure that you do plenty of these. If you have any questions, let me know immediately. We can go through more examples of these, but it's very important that you understand the concepts going on here, because this will be applied now anytime you carry out a synthesis in a lab. Anytime you're wanting to create a product, you're going to be applying these steps, because you do want to try to maximize your yield. So let's look at limiting reactant and percent yield in terms of just moles right now. We won't go to masses quite yet. Here's an example. We start with solid titanium, and we're going to react it with chlorine gas, and we're going to form a solid titanium chloride. We're told that we have, for our starting materials, 1.8 moles of the titanium, 3.2 moles of the chlorine. So notice it's different from the molar ratios. Our ideal ratio is 1 mole of titanium for every 2 moles of chlorine. Excuse me. So what I need to do is look at the actual amounts that I have. Now this is not actual yield, this is actual amount started with. Okay. So this is like my cups of flour and my number of eggs. I want to find the limiting reactant. Which one's going to limit the amount of titanium chloride I can make? Will it be the titanium or the chlorine? And then once I know that, what is the yield, the theoretical amount that I can make in terms of moles? All right, so here's our solution map. How are we going to do this? Well, I start with each reactant. So this is reactant 1, titanium, and I want to convert from moles of titanium to moles of titanium chloride. I do that using stoichiometry. Okay. And remember, stoichiometry is the coefficients in the balanced reaction. Okay, here's reactant number 2, the chlorine. If I had more reactants, I'd do it for each one of these. I do the same thing. I go from moles of chlorine now to the same thing. What is the number of moles of titanium chloride I can make? And in this case, if I go to my balanced equation, I see that there is 1 mole of titanium chloride for every 2 moles of chlorine. Okay, so I'm going to apply those. I have the 1.8 here, and I have the 3.2 here. I'm going to work that out, and whichever one gives me the smallest amount, that's going to determine which one is my limiting reactant. So here's the solution if we work it out, cleaned up a little bit. And 1.8 times 1, I can theoretically make 1.8 moles of titanium chloride from 1.8 moles of titanium. Do the same thing with chlorine, 3.2, and I divide that one by 2, 1.6 moles of titanium chloride. Okay, so this one, there's extra. I have 1.8 moles here. I only have 1.6 moles of the titanium chloride, so this is the least amount of product. Therefore, the 3.2 moles of chlorine, even though it's a larger number, is my limiting reactant. My chlorine will run out before my titanium, and I'm going to have titanium chloride and a little bit of leftover titanium. Now, why do we care about this? Well, hopefully it's pretty obvious, but again, going into industry, most industrial applications are looking to create a product that is cost efficient. The whole point of industry is to make money. These are businesses, and they want to make money. So they want to reduce their cost as much as possible. The more costly the reactant, or the reactant that is most difficult to remove from a product mixture, is usually the one you're going to choose to be your limiting reactant. If it costs a lot of money, then you want to get the most bang for your buck. You want to make sure every scrap of a costly reactant gets used up. And if the other reactants are cheaper, then if you lose a little of those, you're not losing as much money. Or sometimes you have a reactant that contaminates your product. Okay, so the reactant that's most difficult to remove, let's say in the case of the titanium chloride, we want pure titanium chloride when we're finished. And it may be that leftover bits of titanium may be hard to remove. So it's the excess reactant in the previous equation, but if it's hard to remove that titanium from the pure titanium chloride, but it's very easily to remove chlorine gas, we just let it degas, you may choose to make the titanium your limiting reactant. Titanium's pretty expensive too. It's much more expensive than chlorine gas. So choosing which one to use as your limiting reactant is based on very practical applications. The previous example, we looked at finding theoretical yield based on number of moles, but again, we don't measure moles, we measure grams. So we have to add a couple of extra steps. It's the same basic process, we just have to throw those molar masses in there to get to the moles. Let's look at an example of making table salt. Now this is not a reaction that you would normally carry out in a lab setting. Sodium metal, we looked at, very reactive, not something you want to handle very much. Chlorine gas, very reactive, very toxic, but because they are so reactive, they've already done their thing in nature and they've produced lots of abundant table salt out there. But let's use it as our example anyway. So if we look at our balanced equation, and I apologize, your balanced equation in the slides that were put out earlier may not quite be right. The 2 got left out in front of the sodium, but it's 2 sodiums to 1 mole of chlorine yields 2 moles of sodium chloride. Now, let's say we were given 53.2 grams of sodium and 65.8 grams of chlorine. We want to know how much table salt, are we going to be able to fill our salt shaker from these amounts, and what's going to be left over. So which one runs out and how much salt do we make? Let's look at our solution map. We start by finding the limiting reactant. So we're going to take each reactant, reactant 1 and reactant 2, and run it through the same process. I'm going to take that 53.2 grams of sodium, and I can't compare grams of sodium to grams of sodium chloride directly. I've got to go through moles. Moles is my translator. So I get the molar mass from the periodic table of sodium, 22.99 grams per 1 mole. Okay, so now I have the moles of sodium. I need to convert moles of sodium to moles of sodium chloride. So this is where I use my stoichiometry. I'm just going to abbreviate it STOI. If I look at my balanced equation, 2 moles of sodium for every 2 moles of sodium chloride, so 2 to 2. That will give me the moles of sodium chloride, and then I can use the molar mass of sodium chloride calculated from periodic table. Sodium's 22.99, chlorine 35.45. Okay. So that will then tell me how many grams of sodium chloride I can make from reactant 1. I do the same thing for chlorine, reactant 2, so now I start with 65.8 grams. Okay. Now this one's a little bit different because I have to be sure on my molar mass. Notice that's a diatomic, it is a molecule, so don't make the mistake some people make and they just look up chlorine in the periodic table. They get a little confused by that, and so they'll only put 35.45, and it is 70.90. And one other thing I forgot to point out earlier, the other thing you don't want to do, some people right here, they'll say, oh, well, the balanced equation has 2 moles, so they'll put a 2 here. Do not do that. You do not want, let me erase that just so there's no mistaking that. You do not want to put 2 moles of sodium to 22.99. That ratio is always 1 mole to the mass from the periodic table. It's always per 1 mole. Notice everywhere you've got grams to moles, always 1 mole. That never changes. The only time you use those coefficients is when you're doing the stoichiometric conversion from moles to moles. If grams is in there, it's 1 mole. All right, so now let's see, where were we? So grams of chlorine, 70.90 grams, that gave us the moles of chlorine. Now we do our stoichiometry. We go to our balanced equation, 2 moles of sodium chloride for every 1 mole of chlorine, gives us moles of sodium chloride, and then the last step is exactly the same, 58.44. Now notice, once you have the number of moles, okay, as long as you've used the correct stoichiometry, you can compare number of moles as well. You wouldn't necessarily need to calculate the number of grams of sodium chloride to determine the limiting reactant. But in this case, because we need to know theoretical yield in grams, they went ahead and put in the extra step. You would only need to calculate grams for the limiting reactant. Okay, but again, whichever mole or gram is the smallest, that determines which one's the limiting reactant. That determines the theoretical yield. So here's the solution worked out, putting in all the numbers. You can see for reactant 1, we started with our 53.2 grams of sodium. Okay, then we multiply by 1 mole of sodium over 22.99 grams of sodium. So grams of sodium then canceled out. We have moles of sodium. Then we used our 2:2 ratio of sodium chloride to sodium. Moles of sodium canceled out. And then we multiply by the molar mass of sodium chloride. Those moles cancel out. It leaves me with the number of grams of sodium chloride, which when I do the math, turns out to be 135 grams. I do the same thing for the chlorine. Okay, so cancel out grams of chlorine. Then I cancel out moles of chlorine. Moles of sodium chloride leaves me with grams. And I find 108 grams, which is smaller. So the chlorine, again, even though it's the higher mass, is going to give me less product. Now, don't make the mistake of thinking, oh, well, there's a pattern going on here. Each reactant that has the higher mass is the one that has the least amount of product, so I'll just pick the higher mass. That is not always the case either. You have to go through these calculations to figure out which one gives you the least theoretical amount of product. Okay? So our limiting reactant is chlorine, and our theoretical yield is 108 grams of sodium chloride. Now, if we take that theoretical yield and work our way to percent yield, oh, 2 got left out again. Let's put that 2 back in there. So if we're given an actual yield, let's say that we carry this reaction out and we only got 86.4 grams of sodium chloride. So what's the percent yield? Based on the 108, remember we said there were 108 grams for our theo yield. So I take the ratio, 86.4 divided by 108 times 100, and I find that I have an 80.0% yield. Keep an eye on your significant figures as you're doing these calculations. They do start to matter here, and they're going to make a difference. So keep an eye on significant figures. This would be 80.0% yield exactly. I know that sounds, it's 80, why not say 80? Well, there's a big difference between 80.0% and 80.4% in some cases. If you're talking about a huge industrial scale and you just say 80 and it's actually 79.7%, that can be the difference in perhaps several hundred pounds of product if you're producing it on ton scales. So you do want to be as precise as possible when you're reporting your percent yield. So notice the actual yield is less than the theoretical yield because a small amount of product gets lost or doesn't form during the reaction. So again, percent yields, generally speaking, should be, well, they should be less than 100%. 100% should be the maximum you can get unless you have impurities or, well, if you have impurities in your product. If you ever get greater than 100%, you have an impurity in there. If it is much less than 100%, if it's a reaction that is known to go to completion, then there's a problem somewhere. But sometimes we have important reactions, such as a drug synthesis, that actually doesn't get near 100%. Sometimes there are syntheses, organic chemistry in particular, you'll see this, where a good yield may be only 40%. So you're only getting 40% of what you calculate you should be able to get just because of the nature of the reaction. But if it's an important enough compound, then 40% can be usable. That can still be a good reaction. It just depends on what the reaction is. For most of the reactions you'll look at in general chemistry, though, you're aiming for fairly close to 100%. So let's look at an example. Another example, gram to gram. This is example 8.6 in the book. So if you want to follow along, this is on page 263. So you can walk through the written out example there. But the idea here is that we have copper oxide, and it is reacting with, and it's copper 1 oxide. Okay, so if you look at that, there's Cu2O, so oxygen's a 2 minus, this copper has to be a 1 plus. Copper 1 oxide plus carbon, and that is going to yield 2 solid coppers and 1 carbon monoxide. So again, you need to start becoming fluid about looking at these reactions and translating into the names of the compounds. So do keep up, go back and look at your naming, stay on top of that. We'll be using that. We're told that we have 11.5 grams of the copper 1 oxide and 114.5 grams of carbon. And we want to know from those, what's our limiting reactant and what's our theoretical yield. Right, so here's our solution map again. Here's reactant number 1. We're going to start with the carbon in this case. So we go from grams of carbon to moles of carbon using molar mass from the periodic table. We go from moles of carbon to moles of copper using our balanced equation, and then moles of copper to grams of copper, again going to the periodic table. Do the same thing for reactant 2, grams to moles, and moles to grams. So we're using the periodic table, and balanced equation, stoichiometry in the middle. Smallest amount gives us the limiting reactant. Okay. So the only real work here, once you set up your equation and your calculation, is just looking up everything in the periodic table. Looking up molar mass of carbon, copper, calculating molar mass of copper 2 oxide, and then here's copper again we've looked up. So when you work that out, you'll see which one limits you. Now the main conversion factors are the stoichiometric relationships between the moles of each reactant and copper. Okay. And then your other conversion factors are those molar masses you have to calculate. So here's a list of all the things that you need. So you can even make that list ahead of time. What are the relationships you need? These all come from the balanced equation. These are all from the periodic table. Okay, so a balanced equation, a periodic table, and a calculator are all you really need. You don't even really need the calculator, but it saves a lot of time. Okay, so that's what you need in order to solve limiting reactant problems. So let's look at the solution now. Let's plug in all the numbers. So when we run the numbers for the carbon, we came up with 122 grams of copper. And when we look at the amount of copper 1 oxide that we started with and run the calculations on that one, we see that we only got 101.7 grams. So this is our theoretical yield. And our limiting reactant was copper 1 oxide. And again, they're really good at picking examples where the higher mass is the limiting reactant, but it is not always that way. I just want to keep cautioning on that. But this is a really good example. It really brings home how you can't just look at the mass of something and make that determination. If you look, there's only 11.5 grams of carbon here. There's 114.5 grams of copper 1 oxide. There's 10 times as much copper 2 oxide by mass. But if you look at the molar mass of those two, okay, it's more than 10 times as massive. The carbon's only 12 grams per mole. The copper 1 oxide is 143 grams per mole. So it's more than 10 times heavy. So it does kind of make sense that in the calculation, it would end up producing less. Okay? So there's our theoretical yield and our limiting reactant for example 8.6. Now, what if we wanted to find a percent yield for that? Let's say that we only produced 87.4 grams of copper. That was our actual yield. And remember, we said that our theoretical yield was 101.7 grams. Okay, so again, very easy to find the percent yield. I just divide the actual, the 87.4 grams, by the theoretical that we just calculated, the 101.7 grams, multiply by 100, and I find that the percent yield for this reaction was 85.9%. So hopefully this has given you a good overview of how to calculate limiting reactant and theoretical yield, and then if you're given an actual yield, calculating percent yield. Okay, so notice that actual yield is the one thing in here that you don't calculate. You calculate limiting reactant, you determine limiting reactant through a calculation, you calculate theoretical yield, you calculate percent yield. Actual yield is something that has to be given or determined experimentally. So that wraps up those two sections, 8.5 and 8.6 for Chapter 8. Now, the last part of Chapter 8 is Section 8.7, dealing with enthalpy. It seems maybe just a little bit out of place, but it does tie into the idea of stoichiometry, which is why it's in this chapter. We'll look at that in the next section, so look for the next video.